Hello. So we're going to, I think, finish our lectures on distributions today, and we'll finish the topic by talking about distributions. And ordinary differential equations. Okay, hereafter abbreviated as ODEs. Right. So as I've said a few times, it's in the area of differential equations that distribution theory has a lot of its applications, and we're going to look at that in a very in its most elementary context, which is ordinary differential equations that are either scalar or ordinary differential equations in a finite dimensional vector space. The theory can be extended to partial differential equations, okay, and a lot of important methodology arises for partial differential equations using distributions, okay? And I should say that most of the machinery for distributions, using distributions for differential equations, is connected to linear differential equations, okay? So we're going to be looking at linear, constant coefficient, ordinary differential equations. So the most kind of simple class of ordinary differential equations. Okay, so first let's look at scalar equations. Now, differential equations is something that we're going to talk about in more depth when we talk about systems substantially later on. And what we're going to see is that I have some peculiar notation for differential equations, and so I'm going to subject you to that notation now. Okay, so a scalar kth order linear ODE with, and so maybe even let me add something else, kth order linear homogeneous constant coefficient. So there's a lot of simplifications that are happening with these equations. ODE is given by an equation of the following form. F of, so F is a function of the variable, which in this case is a scalar variable, and its first k derivatives. All right, and so and because of these other two attributes of homogeneity and constant coefficient, it has a very particular form, and that particular form is like this. Okay, so it's going to depend on variables x, and I'm going to denote it by x1, which of course is going to be the first derivative. K. Okay, that's the kth order, and it's going to look like this. So it's going to look like a k x k plus a1 x1 plus a0x. Okay, and with a0, a1, a k. So these are going to be constants. And I'm going to ask that ak not be 0. All right. And so if ak is not 0, effectively you can set that to be equal to 1. Okay. And so a solution to such an equation. Okay, so when I talk about differential equations, I'm careful to talk about equations. Okay, so the equation here for me is this thing, and solutions to the equation. Okay, and so an equation is a function of these variables, and these variables you should think of as being independent scalar variables. So these, these could be, I could just as well write x1 I could just as well write x1 for x and sort of forgo the derivative notation. So the point is that this is an independent variable in the argument of capital F, as is this. All right, so this is a function of these k+1 variables. All right, and so that's what a differential equation is. It's a function. Okay, and it takes values in R. Okay, so a solution to a differential equation like this is a mapping C. Okay, and so this is another piece of differential equation weirdness that I do, is that I denote the variables by x and the functions of t by c. Okay, so a few times I've written differential equations and I've written x dot of t. I generally don't do that. I distinguish between x, which is a constant, and c, which is a function of t. Okay. All right, so c is the solution. Okay, so it's a function of t is the main point. So a mapping that satisfies. Okay, so it satisfies f of c of t, and then so let me so c1 of t. Okay, so you should be careful. The one here and the one here, they're meant to look the same because I want them to be thought of in a similar way. But this is just a label for a scalar variable, and this is the derivative of this function of time. Right, so this is potentially confusing, but that's how I do it. And I ask that this be equal to 0 for all t, and the t lives somewhere. I'm not going to fuss too much about that right now. Okay, so for example, could be defined on all of R. Okay, and so therefore, okay, using the specific form of capital F, like so, and so you see here that if you set this equal to 0, you could divide through by ak, and so therefore you're going to get the highest order coefficient here to be 1 without loss of generality when you're talking about this equation, and so we're going to do that. We're going to assume now that ak is equal to 1. Or equivalently divide through by ak, because I'm assuming that it's not 0, and then redefine all of these other a's to be a0 is a0 over ak, and so on. And then my equation looks like this. My solution, so the condition, sorry, for a solution looks like this. Okay, so this now, except for my overly pedantic choice to not denote the variable by x, but by c. This is an equation that you would have studied in your elementary differential equations course. And so there's all kinds of techniques for solving this equation. You assume a solution of the form c of t equals e to the rt. You find the roots are as the roots of some polynomial whose coefficients are these a's, right? And then you have to fuss with situations where a root has a multiplicity, okay? And then you have to also fuss with complex roots, okay? But these are things that I just assume that you've seen before. All right, so we know how to solve an equation like this. Okay, so such an equation admits unique solutions if one specifies enough conditions on the solutions. And the way that we're interested in doing that is by specifying initial conditions at some time. Let's say, just to be concrete, let's say at time 0, okay? Actually, sorry, for the purposes of this general discussion, let me make it an arbitrary time, okay? So if we specify c of 0 equals, let's say, x0, okay? So this is now just a scalar constant, okay? c1, the first derivative of c with respect to t. Sorry, I got this all mixed up now. Okay, so at t0 is x0, 1 up to c k minus 1 of t0 equals x0 k minus 1. Right, so these x0, so again, these are numbers, okay, and despite the fact that I'm using that just means that this is the initial condition corresponding to the first derivative, okay, but all these are just numbers, okay. All right, so you specify these initial conditions at some time t naught, and we're going to mostly be interested in t naught equals 0. Okay. All right, so the fact is, if you specify these conditions, then there is a unique solution of that equation, okay? Now, that's just sort of a very quick overview of differential equations. And so let's call this equation, for the moment, let's call this equation 1. Okay, there's probably going to be an equation 2. Okay, so we wish to consider equations like 1 for determining solutions, but with a right-hand side being a distribution. Okay, so let's think about what that might mean. Okay, all right, so this equation, as I specified up here, is homogeneous, and homogeneous means 0 here. Okay, now inhomogeneous would normally mean that you have some function f of t here. Okay, and then you want to solve this the same differential equation by specifying its initial conditions with some f of t. All right. Now, and so in your differential equations course, you would have studied very specific solution methodologies for specific kinds of f of t. So basically, solution methodologies in situations where f of t has the same form as comprise the solutions of a differential equation like this. And so basically that means functions of t that are linear combinations of functions that look like this. T to the k, e to the alpha t, cosine beta t, or sine beta t. Okay, so you would have learned how to find solutions of equations for f's that look like that, and that gives you some little party trick that you can play with getting solutions of this differential equation. So it's a party trick and also a way to score points on exams. But I've never felt like that was the most interesting part of thinking about differential equations, but that's typically what you learn in your first differential equations course. Now what we want to do is we want to put a distribution here, and I'm going to call that distribution beta. Okay, so now this is very much a different kind of a beast. Okay. And so in particular, if you have a distribution over here, then it's very much not clear what an equation like this might even mean, because these things are functions of time, and I have a distribution over here. And I know that functions, locally integrable functions at least, can be thought of as distributions, but how do I know if I choose a distribution over here that I'm going to get a solution which corresponds to the distribution of a function? Okay. And so what you have to do is you have to consider the solutions of the differential equation as themselves being distributions. Okay, so we seek solutions that are distributions. Okay, so that is, okay, so given a beta, which is a distribution. Okay, so beta is going to be my right-hand side here. Okay, I want to find a solution, theta, in distributions that satisfies theta k. All right, so it satisfies the same differential equation, but now with theta in place of c. Okay, so I certainly don't want to write theta of t. Okay, so that's the objective here, right? So by changing the problem into one of distributions, now it's rather not clear at all what's going on here. Just, can you find solutions? Can you find unique solutions? If you can find unique solutions, how do you prescribe conditions under which the solutions are unique? Because I can't do this anymore, because these initial conditions involved evaluating my solution at a time t naught, and distributions are not functions which can be evaluated in general. Okay. Right, so I'm not going to talk about, there is a way that you can develop this theory of scalar, linear, constant coefficient, inhomogeneous differential equations in the space of distributions. And it goes just a little bit beyond how deep I want to get into anything here. So I'm just going to tell you some answers. Okay. All right. And it's actually not that hard to prove this theorem that I'm about to state to you. But as I say, it would take a few lectures to develop the machinery to do this. And so, for example, one of the things that you have to sit and carefully develop is what's known as the theory of convolution. And we'll talk about convolution, but you have to dig relatively deeply into the theory of convolution in order to prove this theorem. Okay. So let's, oh, and I should say, sorry, I didn't say this, but let me sort of just kludge it in here because this is where it belongs. Just some terminology that I often use when I have a differential equation F like this that involves the highest derivative of my, the order of my differential equation, in this case K. I will normally write F hat as the thing you get from solving this equation for the highest order derivative. Okay, so I'll write F hat of x, x1, xk minus 1. Okay, and for us, this will be minus, okay, because I'm solving for the highest order derivative here, right? So I'm solving for that in terms of the other things. So everything becomes a minus. Minus a0 x minus a1 x1 minus a, oops, a k minus 1 x k minus 1. Okay, and so the other way to this, another way to write this, in other words, is that and so it's going to get too crowded for me to fill it in here, so I'll just sort of do it in red. So it's going to be the ck is equal to f hat of ck minus 1, like that. Okay. All right. So again, just notation, and it's just because it's a funny way I think about differential equations. All right, so the point is, I'm going to let f hat, and so instead of f, I'm going to use f hat because f hat contains the information you kind of care most about. Okay, let f hat be a scalar, linear, constant coefficient, ODE. Oh, and so, sorry, it's also homogeneous. So f hat is homogeneous, although I'm going to solve associated to that an inhomogeneous problem. Okay. And let beta be some arbitrary distribution. Okay. All right, so if, okay, and so this is going to be, sorry, I shouldn't have done this. I'm not actually interested in this equation. I'm interested in this equation. Okay, so if, so for the equation, so first of all, let's state conditions for the existence and uniqueness of solutions. Okay, so let's let the solution set of f hat and beta be all those distributions that satisfy 1. Okay, so sol is going to be the set of solutions of distributions satisfying 1. Okay, so I have a bunch of things that are true. So first, no matter what, there are solutions to equation 1. Okay, and there are many of them, possibly. In fact, there's at least two, depending on what beta is. Okay, so the cardinality of the set of solutions is two. Is greater than or equal to two. All right, so there is a solution, and there may be multiple solutions. Okay. All right. Now, if beta is a distribution which is supported, whose support is bounded on the left, okay, then there is a unique solution so the cardinality of the set of solutions whose support is bounded on the left okay, is equal to 1. Okay, so I get uniqueness of solutions if A, the inhomogeneous term beta, okay, so inhomogeneous term beta has support bounded on the left, and I seek solutions whose support is similarly bounded on the left, okay? And the same thing is true for bounded on the right. So I'm writing F here. I most often care about R. But there's nothing stopping you in general from considering F. Okay. All right, and so similar, you have a similar result for support bounded on the right. Okay, so solve F hat beta intersect D prime minus. All right, so you get uniqueness when you restrict the support of the inhomogeneous term, and you similarly restrict the support of the kinds of solutions that you're going to consider. Okay. All right, nice. Okay, now, what I want to do now is I want to work out in detail what this a special case of part 2. Okay, so I want to consider a particular distribution whose support is bounded on the left, and I want to seek a solution, the unique solution of that corresponding differential equation in distributions, the unique solution whose support is bounded on the left also. Okay, and the distribution that I'm going to talk about is the Dirac delta. Okay, so we're going to consider case 2 when beta is delta. Okay. All right, and so what we're going to show is this. Is the unique solution, and I know it's unique by the theorem I just stated, but didn't prove. Okay, so the unique solution to the distributional, scalar distributional differential equation 1, when, so the unique solution in the set of distributions whose support is bounded on the left, when beta is equal to delta is, okay. So it actually turns out to be the solution, although the equation is an equation in distributions, the distribution that you get as a solution is actually the distribution corresponding to a function. And I will tell you what the function is. Okay, it's theta f where, okay, so the important thing that I've said so far is that even though the inhomogeneous term is a distribution, because of the very simple nature of the distribution, the solutions are still functions. Okay, where f is c of t okay, so f comes in a very specific form. Okay, and the form is that I take a product of two functions, one being this thing c, which I'm going to tell you what it is in a second, and this is the step function that I talked about last time, and I waffled around last time with whether there was a subscript on one here, and in the notation that I seem to use in this course, there is a subscript for the step function, and that's what it is. Okay, so but I'll tell you what that is now. So and where 1 of t is the thing which we talked about last time. So it's 1 for t greater than or equal to 0, and 0 for t less than 0. And so what's c is the unique solution to the homogeneous ODE. Okay, so I have some homogeneous ODE prescribed by f hat here. Okay, so given by these coefficients a here. So it's the unique solution to the homogeneous ODE corresponding to a very particular set of initial conditions. So the initial conditions are the c of 0 is equal to 0, c1 of 0 is equal to 0, and then all the way up to c k minus 2 of 0 is equal to 0, and then the last one, the highest order initial condition, is the k minus first derivative at 0 is equal to 1. Okay. All right, so let's prove this. So uniqueness here comes from part 2 of this theorem that I haven't proved. Okay, so I'm just going to prove existence here, and I'm going to prove existence simply by showing that this with f, but like this distribution satisfies the equation with that as delta as the inhomogeneous term. Okay. So this is just a direct calculation using rules for distributions, but I think that's worth doing. Okay, so let's make a couple of observations to get started. Oops. Okay, so first is that theta of the step function c, okay, because that's what I'm talking about here, right? Okay, so this is the function that corresponds to my proposed solution. Okay, I claim that this is equal to c theta times the step function. All right, so let's make sure we understand what this means. This meaning is unambiguous. Okay, this is a locally integrable function. This is the distribution corresponding to that locally integrable function. Now, what's the meaning of this then? Okay, well, c is a solution of the differential equation, satisfying those conditions. Now, the form of solutions of that differential equation is, linear combinations of products of polynomials with exponentials with trig functions. All right, and the point is that such an C will be infinitely differentiable, just because all of the components of the solution are infinitely differentiable polynomials, exponentials, and trig functions. Okay, and so this now is the distribution corresponding to that locally integrable function, and this is the product with the function C that we talked about last time. So you can take any distribution and multiply it by an infinitely differentiable function, right? So we talked about that last time. Okay, and so what I'm claiming here is this is true, right? And let's prove that since it's elementary. Okay, so oops, theta, greater than or equal to 0. C of phi is, by definition, the integral over R, 1 greater than or equal to 0, C of t, phi of t dt. Right, and this is equal to, okay, and so the point is that the one greater than or equal to 0 applies not to just C, but to C times phi. Okay, and so the point is that this is equal to theta 1 greater than or equal to 0 of C phi. Okay, and by our definition of this, okay, which we talked about last time, this is C theta of 1 of the step function of phi, right? So that proves that this is equal to that. Okay, another observation. Okay, and this observation is a general one about distributions that are obtained as products of infinitely differentiable functions and distributions. Okay, and the claim I'm going to make is this: that if theta is any distribution and if f is any infinitely differentiable function, then the derivative of this distribution, okay, right? So this means the product of this distribution by this infinitely differentiable function, just like we talked about last time and that I'm also using up here. Okay, so I claim that the product rule is satisfied. All right. Okay, so let's prove that. Okay, so certainly I know that if phi is a test signal, then I know that f phi, this is just the usual product rule. Okay. All right, so now I just calculate using definitions of everything, but it's an instructive exercise. Okay, so f theta 1 of phi. Okay, and so what I want to show in the end is that it's equal to that of phi. Okay, so now I use the definition of derivative, and so this is f theta of, minus f theta of phi 1, and that's minus theta of f phi 1. Okay, Now I'm going to use my formula here. Okay, so I have FV1. I'm going to, solve for minus FV1 because that's what I have here. Okay, so this is equals theta applied to, so it's going to be F1 phi minus F phi 1. Okay. All right. Okay, so distributions are linear. So this is theta of F1 phi, okay, minus theta of F phi 1. Okay, now I use my rule for multiplying distributions by products, right? Okay. All right. So this is going to be the same thing as this distribution multiplied by that infinitely differentiable function evaluated on that test function. Okay, so this is, in other words, F1 theta of phi. Okay, and here in the second component, I'm going to use the definition of the derivative, right? Because here I have this test signal with the first derivative. And so by definition of the derivative, this is plus, so I get two minus signs that cancel out, theta 1 applied to F phi. Okay. And then I can finally simplify this second one. Okay, so it's F1 theta of phi plus F theta 1 of phi. Okay, and that's what I wanted to show. Okay, all right, so there's a couple of observations that we're going to use in our calculation. Okay, all right, so carrying on with the proof proper. Okay, so what I need to do is I need to show that the this distribution satisfies this differential equation with the delta there. Okay, so what that means is that I just need to calculate all the derivatives of my proposed solution, and so that's the first part of the proof, is just calculating derivatives and seeing what they are. All right. So theta, one step function, c, first derivative of that. Okay, so let me make that maybe clearer. All right, so this is c theta 1. Okay, now this is just the definition of, well, sorry, this is just part 1 here. Okay, now I'm going to use part 2, okay, which is the product rule. All right, so this is C1 theta 1 greater than or equal to 0 plus C theta 1. Okay, and last time we calculated this derivative. Okay, so this is the derivative of the step function. We showed last time that the derivative of the step function was the Dirac delta. Okay, so this is C1 theta 1 greater than or equal to 0 plus C delta. Okay, now what's this? Okay, so this, okay, is obtained by C delta of phi, equals delta, by definition of multiplication of a distribution by an infinitely differentiable function. It's that, which is C of 0, phi of 0. That's the definition of the Dirac. Okay, and my initial conditions ensure that that is equal to 0. Okay, so the upshot of all that is that this this term will be 0. And so you just get C1 theta 1 greater than or equal to 0. Okay, now you can basically just repeat that calculation. Okay, k minus for the first k minus 1 derivatives. Okay, recursively. Okay. Theta 1 greater than or equal to 0, C, right? So these are my proposed solutions of J is equal to C J theta of the step function. Okay, and this is true for J going from 0, 1 up to k minus 1. Okay. All right, and then finally you need the highest derivative. And that one turns out to be different, you know, in kind of an obvious way, but let's calculate what that way is. Okay, so you have that theta of the step function times C of k. Okay, and so what I'm going to do is I'm going to look at this equation with J equals k minus 1, and I'm going to differentiate that, right? Okay, so what I'm doing is I'm differentiating this thing with J equals k minus 1. All right, and I'm going to use all the rules for doing that. Right, so what that means is I'm going to use the product rule. So I'm going to get right, so I'm going to get the derivative of this thing. Okay, again with J equals k minus 1, so that's going to be ck. Okay, times the Dirac, or sorry, the step function, plus c k minus 1, and then it's going to be the derivative of this, but the derivative of this, as we've already seen here, is delta. Okay. All right, and then this one now. Okay, so I'm going to evaluate that exactly like I did here, but I get a different answer. So this is C k minus 1 delta. Okay, so what is that as a distribution? Well, I act on a phi, and so this is delta of C, sorry, it's k minus 1. Like so. And so this is C k minus 1 of 0 phi of 0. Okay, and so from that, okay, you can conclude, and this is 1. That's what the initial conditions are, and so the point is that this is equal to 1. Sorry, not 1. It's equal to delta, right? Because the point is that this thing acting on a phi is just going to return phi of 0. So that's what the Dirac does. Okay. So then now I've calculated all the derivatives, then just substitute into the differential equation and ask, is it satisfied? Okay, so I get that 1 greater than or equal to 0 c plus a k minus 1 theta k minus 1 1 greater than or equal to 0 c plus A1 theta 1 greater than or equal to 0 C plus E0 theta 1 greater than or equal to 0 C. Okay, so now you just substitute all of the derivatives that I just calculated. Okay, and what you get is, right, right, so all of these derivatives, except for the top one, are just going to come in a form like that. Okay, so this is going to be CK plus AK minus 1 CK plus A1 C1 plus A0 C. Right, so that whole thing is some infinitely differentiable function. Then they all get multiplied by that distribution. Okay, and then I get the remnant delta, which shows up from the highest derivative. Okay, plus delta. Okay, and now the point is because C is a solution of a homogeneous equation, that is equal to 0. Okay, and so I've verified that that thing is a solution of the differential equation. All right, so that is in, kind of some expansiveness, verifying what the solution to a particular kind of differential equation is for a particular kind of distribution right-hand side. Okay. Okay, good. Now we want to do the same thing, but not for a scalar equation, but for a system of equations. Okay. Okay. And so here, I want to have a first order. Okay. So we have a first order. Okay. So first, sorry. I take a finite dimensional real, could be complex, but let's make it real, and let's see if I can stick to R instead of F. Okay, so let X be a finite dimensional real vector space. Okay, so Rn, for example, but I find it's easier to not work with Rn. It's easier, certainly less confusing, to work a little bit more abstractly with a general vector space than to work with the concreteness of Rn, because Rn has all kinds of structure that is only distracting when you're talking about systems of differential equations. Okay. So let's first define the kind of differential equation we're looking at. So a first order, okay, system of linear homogeneous constant coefficient ODEs is a map. Okay, so in the scalar case, everything was a scalar, but now I have to be a little bit more careful. So it's a map which takes okay, so it's two copies of X, the vector space X, and the variables in there I will write as X and X1. Okay, and it's going to map to F of X and 1. Okay, and the specific form of that in the case of a linear homogeneous constant coefficient ODE is x1 minus ax. Okay, for A is a linear mapping from X to itself. Okay. And the solution is T goes to, and again, I'll write, I distinguish, so X here is an element of the vector space. Previously, they were scalars, but now they're elements in the vector space X. So X1 is in X and X is in X. Okay. And a solution is a curve in X satisfying f of c of t, c again, first derivative of t equals 0. And this simply means that c1 of t is a of c of t. Okay, and you may be more familiar with this kind of an equation as x dot of t equals a x of t, where x is a vector in Rn and a is a n by n matrix. Okay, again, I prefer to do this in the more abstract setting of vector spaces. I think it's less confusing. Okay, good. So this is my inhomogeneous differential equation, and again, we want to solve this equation in distributions. Okay, and I'm going to just give a I'm just going to sort of cut to the chase and assume a certain kind of distributional input, just like I did here, some kind of a Dirac. Okay, but I need some notation for doing that because everything here is vector valued. Okay, so we consider a distributional version of this equation of this ODE with inhomogeneous term. Okay, so just like in the other case, the inhomogeneous term gets added here, and normally I guess that might be called like B of t or something, or F of t, whatever. And normally, that'll be a function, and then you might have some methods for solving that equation. For example, the variation of constants formula. Okay, and you have methods of solving the homogeneous equation, and that all comes down to calculating the matrix exponential. And I'm just like I did in the scalar case, I'm going to assume that you know all about solving this this homogeneous differential equation in terms of the matrix exponential. So I'm just going to use that. Okay. And so we're going to be considering an inhomogeneous version of this equation with some kind of a distribution here. But we have to have some notation to bookkeep the fact that this distribution isn't going to be a scalar value distribution, but a vector space value distribution. So we have a bunch of notation to introduce to make things work. Okay. All right. So we consider a distributional version of this ODE with inhomogeneous term given by, and I'm going to sort of say this loosely before I define it precisely, Dirac in some direction. In X. Okay, because again, I have my equation takes place in a vector space, it's not a scalar. Right, so notation. So I'm going to introduce some kind of fancy looking notation for things which are not that fancy. But the notation is fancy. Okay, so first, an X valued distribution is a continuous linear mapping, just like a distribution is. But of course, it takes its values at X. Okay, so theta from test signals. And here I'm going to restrict to R. And again, you could consider X to be F and F vector space and do everything there. It doesn't make any difference to the general theory. Okay. All right, so let's make sure we understand this. This is a vector space. This is a vector space. Okay. This has a topology. And so the topology of X is a finite dimensional vector space. So you can put any norm you like on X and it'll define the same topology. And so we talked about that when we talked about norms, right? So all norms on a finite dimensional vector space are equivalent, right? And we sort of express that by saying that we have a formula like this relating two different norms. Okay. Okay, so the point is that that statement has meaning. Okay, we can talk about continuity because we have a topology here and we have a topology here. Right, and so continuity will mean rather the same thing as it did for distributions, which is that if you have a sequence here that converges to 0, then when you apply theta to that sequence that converges to 0, you'll get a sequence here that converges to the 0 vector in X. Good. That's part one. So sorry, notation. So you use the obvious notation for these. Okay. The next thing we need to talk about is this idea that I mentioned up here of a Dirac in some direction. Okay, and so you can talk about, generally speaking, some scalar distribution in a direction, and we have just some funny notation for that. Okay, so the direction is going to be represented by, let's say, x naught. Okay, and we take a distribution a scalar distribution. Okay, and what I'm going to define is I'm going to define a vector distribution associated with that. Okay, and I write that thing in this way. Okay, so the symbol I use, sorry, not delta, theta. Okay, the symbol I use is this thing which is pronounced tensor. Okay, and it is intended to be suggestive that there is a framework here that I'm talking about, but I'm not really talking about it. And that's that this distribution can be thought of as a tensor product. Okay. Okay, so, but for our purposes, this is just a bit of notation. Okay, so I need to tell you how to define this distribution, and it has the obvious definition. That x0 tensor theta applied to a test function phi, right? Because that's what you need to do to get something in D prime, right? You need to take a test function and apply it to get a vector. Okay, and the vector is simply going to be theta of phi x naught. Okay, so it's just a scalar multiplied by the vector x naught. This is a very simple thing with just a funny bit of notation attached to it. All right. A corresponding bit of notation is this. Okay. If C is a C infinity mapping from R into X, okay, and theta is again an arbitrary distribution. Sorry, it's a scalar distribution. Okay, we're going to define and it's going to be another tensor-y thing. Okay, so it's going to be C tensor theta, and this is going to be, so theta is scalar valued, C is x valued, the tensor product here is going to be x valued, so it's going to be d prime of r x, okay, and it's going to be defined like this. Okay, so what you're going to do is you're going to actually let me do this in a slightly more sophisticated way from the way I sometimes do it. Okay, and that is by requiring that for lambda in the dual space of X. Okay, so this now, when we talked about duals for distributions, we talked about algebraic and topological duals. X is a finite dimensional vector space, so the algebraic and topological duals are the same. Every linear map on from a finite dimensional vector space is continuous. All right, so the algebraic and topological duals coincide. All right, so for every lambda in X star, we have, okay. Okay, so you take lambda, okay. All right, so this thing is a distribution in X, okay, and so it therefore takes a test function and gives you something in X. Okay, and so we have, okay, sorry, I'm going to use notation that we understand. Okay. Okay, so let's make sure we understand what's going on here. This is an X value distribution. This is a test signal in D. Okay, so the resulting thing will be a vector in X. Okay, and lambda is a linear function on X, an element of the dual, and so that's what that is. Okay, and this is equal to lambda of C. Okay, so tensor, sorry, let me just do this times theta. All right, so let me see if we can understand what this means. So this is now, I'm going to take my vector valued function C, right? So it's an infinitely differentiable function with values in X. I'm going to apply to that function lambda. Okay, so this is going to be an infinitely differentiable scalar function, and I can multiply that by the distribution. All right, so that's a way of defining that. Let me just be slightly more concrete about that. And it's equivalent to what I just said, but a little bit easier to understand maybe. So it's a little more less elegant also. right? So this infinitely differentiable vector valued function can be written as a linear combination of the basis vectors times coefficient functions, which are linearly independent, sorry, which are infinitely differentiable. Okay, so C1, C n in C infinity of R. Okay, and so then we define, okay, so C tensor theta to be, okay, C1 theta plus, sorry, E1 plus Cn theta En. Okay. All right. So remember, what we need is a distribution, right? And an x valued distribution. And so these will be scalar valued distributions, right? So it's the infinitely differentiable function c1 times the distribution theta. Okay. And similarly all the way up to n. All right, so these are scalar distributions, okay? And so then I'm taking the scalar distribution in the direction of E1 and then up to En, okay? All right. Okay, so the final bit of stuff that I need is, get my numbering correctly. Okay, so if A is a linear mapping on X, and if theta is a distribution, okay, we can define A of theta to be a distribution on X, okay, by, again, the obvious formula. So A of theta, okay, applied to phi is A of theta applied to phi. Okay. All right. So this is defining this as a vector value distribution. So it takes a scalar test signal. Okay. And it does it by applying A to the vector that I get by applying theta to that scalar test signal. Okay. All right. Now, with all of that notation, then I can finally say what I want to say. Okay. So then, theorem. Oh, so maybe let me say it this way. Okay, so we want to consider the distributional ODE theta 1 plus A of theta is equal to beta. Okay, and here beta is some given vector value distribution. And our solution, theta, should similarly be a vector valued distribution. Okay. All right, so we're going to do that in a special case, just like we did for scalar equations. Okay, and I'm going to call this equation 2. And I apologize for my number formats here, that these look like those. When I do this in LaTeX, it doesn't. Okay. All right, so the distribution theta f in d prime of r x with, okay, so again, as with scalar equations, I'm going to choose beta to be delta. And when I do that, then the solution is a distribution coming from a function. Okay. And there's, of course, just like in the scalar case, going to be a specific function which gives rise to that. Okay. So with f of t equals step function times c of t. Okay. And beta equals Dirac. Sorry, my notation for this is I'm going to take the Dirac in the direction of x naught. Okay. Okay, so I need to prescribe all this stuff, right? So the solution is theta f with f looking like this. Beta is going to look like this. And so the last thing I need to do is tell you what c is. So I kind of did this in an awkward order, and I apologize. I should have put that first, but okay. And with c being the solution to the inhomogeneous equation, sorry, to the homogeneous equation, with initial condition x naught. Okay. Okay, so I apologize. I said this in an awkward way, but so I have this equation, okay, with beta equal that, first of all, so I've chosen some x naught, and I've taken a specific inhomogeneous term that looks like this, okay. I'm saying that the solution to that equation is of the following form. So it's theta f, where f is just like it was in the scalar case. It's a product of the step function with some solution to the inhomogeneous equation. And in this case, the solution is uniquely specified by that initial condition. Okay. So that distribution is the unique solution to in d prime plus of r x. Okay. And the proof is rather similar, but just involves all of our notation. Okay, it's a bit easier because you only have to calculate one derivative. Okay. All right, so first we notice that we notice a few things. And so let me write down these few things to start out with. So in other words, you would start to do this calculation, and as you went along, you would see that you'd need to figure some stuff out. So let me put the stuff that you need to figure out first, so you can just do the calculation directly. Okay, so the first observation is that theta c is c theta. Okay, this is exactly analogous to the similar thing that we had in the scalar case, right? So in the scalar case, we had, excuse me, we had that. Okay, and it's precisely the same kind of formula. And it's proved in exactly the same way. Right. The next observation is that with C as in the theorem statement, okay, C tensor delta is equal to x naught tensor delta. All right. And the way you prove that, it's rather the same as, okay, so again, it's just the same with extra fun notation. Okay, it's exactly the same as what we did for this calculation here, right? So we ended up with delta. The only difference now is that C, K is equal to 0. Sorry, K is equal to, K is equal to, right, K is equal to 1 in this case. And so the this K is equal to 1. And so K minus 1 is equal to 0. And so this is the initial condition, which is X naught. Okay, so that's where you get X naught times delta rather than just delta, which we got here. Okay. Right, but it's the same computation. All right. All right. The other thing we want to prove is, all right, so I'm proving that this is the solution, okay, and this is equal to that. And so, we need to be able to differentiate that, okay, and unsurprisingly, you differentiate that using the product rule. Okay, so C tensor theta. And in fact, this is true for any distribution, but let me just do it. Okay, is equal to, okay, so the, sorry, let me do this, let me make the general statement because that's less confusing. Okay, so the general statement is that F tensor theta 1 is F1 tensor theta plus F tensor theta. And then we're going to calculate this in a specific case. And this is true for any F. So I'm going to have to make sure I did this right up here. Oh yeah, sorry. I was concerned that I did this here for vector distribution, but I didn't. Okay, good. So F here is a vector function, which is infinitely differentiable. And theta is a scalar distribution. Okay, so that formula is true. So that's the product rule. And again, that's proved exactly the same way as we proved it in the scalar case, just one of the terms is vector valued. Okay, and then finally, we have that, again, if you have a vector function, and a scalar distribution, then A of this vector distribution is A of F with the scalar distribution. Okay, all right, so those are the observations that I'm going to make use of, and making use of them, the rest of the theorem follows easily. Okay, so we calculate. Okay, so our distributional equation is this one, right? So I need to calculate that. Okay, all right, so again, I'm assuming that I have a solution in the form that I have stated. So that means that this is 1 greater than or equal to 0, C. Okay, so we have theta 1 greater than or equal to 0, C, first derivative. Okay, so now I use my statement 1. Okay. Okay, then I use the product rule. Okay, and I notice, just as I did in the scalar case, and as we proved last time, the derivative of the step function is the Dirac. All right. Okay. And now C satisfies, is a specific solution of the homogeneous differential equation with this initial condition. Okay. And so as we saw in observation 2, that means that this is that. Okay. Okay, and okay, so so this is C1. Theta 1 equals 0 plus x0 times Dirac. Okay, and then, so therefore, and so let me just also calculate A of this thing, okay? So A of theta 1 greater than or equal to 0 C is, okay, so I use part 1 again, and I substitute that. It's A of C tensor theta step function. And then I use part 4. This is A of C tensor step function. Right? And therefore, you calculate that theta 1 plus A of theta 1. All right, so now it's just a question of substitution. Okay, so I have this term here, and I have this term here, and then separately I have that. Okay, so it is C1 plus A C tensor theta 1 greater than 0 plus x naught tensor delta. All right. And now, because C satisfies the homogeneous equation, this is equal to 0. Okay. And so there, it satisfies the differential equation. Okay. And uniqueness, I didn't state it, but you had this theorem up here. About uniqueness of distributional solutions that I stated in the scalar case. It's unsurprisingly also true in the vector case. Okay. All right, so that's what I'm going to say about distributions and differential equations. And we're going to see that these differential equations with Diracs as in homogeneous terms are quite important, but we'll get there when we get there. So I think, unless I remember something important that I forgot, that's all we're going to say about distributions. And next time, we're going to start talking about convolution.